Hi everybody. Hope you're all having a good day today so far. Today we are going to talk about addition of sets in a vector space, and we'll also be talking about production, how to model production in a technically and analytically useful way. We'll be talking about profit maximization for firms, and we'll be doing, I think, our first optimization theorem. It'll be a useful optimization theorem about aggregation. So it will be useful when we're talking about, for example, aggregating across a bunch of firms in the industry or in the economy. So let's start right off with an example. And this example is going to have two firms, but you can think of it as lots of firms if you like. Be kind of representative of a situation with lots of firms. So here we have firm A. In firm A, firm A's production possibilities are described by a production function, and the same for firm B. Not very colorful names for the firms, but we can live with firm A and firm B. Firm B has also a production function, not necessarily the same as firm A's. So this is, of course, the amount of output. Y is the amount of output in each firm's case, and this is the amount of input in each case. And we're actually going to do a specific numerical example here. So this we're going to say is 1/2 times z, and this is going to be the square root of z. Let's draw a little diagram of each of these production functions. So for firm A, the production function looks like this. This is z, this is y, and this is the graph of the production function. And for firm B, we have a production function that looks about like that. And it will actually be useful to think of a concrete example here. Let's think of the input here as steel in each case. So measured in some particular units. And let's say the output is trucks. So each of these firms uses steel as an input to produce trucks. But each firm produces them using a different production process, and that's why we have different production functions for the two firms. This is the story that we have if we have a single input and a single output. Now suppose that instead we had a firm that produced more than one kind of product, more than one kind of output. Let's say one of these firms produces both trucks and cars using steel. Then we would have to do something like the following. We would say there are two kinds of output, let's say, for this firm. The firm can produce trucks, and it can produce cars. And I've used Y in each case because here I used Y for notation for the output. So here we have two different kinds of output. And now, for the amount of steel used, or in fact, Z in this case could actually be multidimensional. Z could be a vector describing the amounts of a whole bunch of different inputs, steel, but lots of other things too. But for any given vector of inputs, input quantities, presumably the firm here could vary the mix of trucks and cars. So let's draw a kind of I guess we could call it a production possibilities curve here. And this would be the set of all possible production combinations, trucks and cars, that we could get from some given specific z vector. So z could be one-dimensional, just steel, but z could be multidimensional. It could be a whole vector of inputs. And the firm now has the ability, the flexibility, to produce mostly trucks or all trucks, produce mostly cars, or something in between according to this production possibilities curve. Or, of course, something down here as well. Could actually produce inefficiently, could produce down in here. But the point that I want to make with this two output example is that using a production function isn't going to work anymore, because now we would have y1, y2 is some function of z. Let's suppose it was firm, maybe this is firm C, some other firm. But now for any given z, we have a whole bunch of different possible y's. So this isn't a function anymore, because a function assigns a specific amount, a specific number to any argument that we put into the function. So this wouldn't be a function. So the production function approach to describing firm's production might work fine if we only have one kind of output. But if we have more than one kind of output, production function approach really isn't going to work. So what we do in this case is we don't use the production function as a way to represent the firm's production possibilities. We use the set of production possibilities. This wouldn't be it here because this only has the outputs. But back here, where we have only the one input and the one output, I would use capital XA to describe all of the ZY pairs on or below the graph of the production function. And here, for firm B, I could call that XB, and in fact, I could write these as XI equals the set of all Z and Y in R2 plus such that Z, and I should make that Y. Let's take that off and make that a Y. Such that Y is less than or equal to f of z, and I want to put an I in there because I'm talking about firm I, and I want to make sure it's clear that's a capital X. And I could do that for each firm I. And so that would be the set that I've drawn here as capital XA and capital XB. And notice it's the set of all input and output pairs that the firm can produce, described in this case by a production function. But more generally, we wouldn't have a production function. We would just say capital XI is the set of all input and output combinations. So this could be a vector, this could be a vector, and this would be in R plus N, or even N plus M, right? So, but we wouldn't have this on the right-hand side. We'd simply say X is the set of possible input-output vectors, the set of possible production plans for the firm. So that's the first step in modeling production differently than with a production function. Notice it doesn't rule that out. If we really do only have one kind of output, we can use a production function to represent this, and as we have down here, that's consistent with the set of things below the graph. But this is clearly then more general. So that's a first step in modeling production a little differently. Now, I said a little earlier that we're going to be interested in aggregating across the firms. So you can imagine just the two firms or a whole bunch of firms. And I want to find out what are the aggregate production possibilities from all of the firms in terms of what, if we put in inputs into all the firms, what are the possible combinations of outputs that we could possibly get. And the way we'll do that is now without using these production functions, but instead using these production possibility sets, input-output sets, we can aggregate across the firms by simply saying capital X now in the same space. So this is R2 in this example. More generally, it could be Rn. This would be the set of all the aggregate input-output vectors that are possible, and that would be equal to the sum of the possible input-output vectors for each of the individual firms. And if I had more firms, I'd have more capital X sets that are being added. And so that's the way that we will model production and the aggregation across firms. But notice we haven't actually given a definition of what this is. So now let's write down a definition of the sum of two or more sets, and then we can use that definition to go a little further in our modeling of production and then profit maximization for the firms or in the aggregate. So let's see here we have a definition of the sum of, in this case I've just got the definition of the sum of two sets, but it's obvious I could, if I wanted, I could write the definition as the sum of n sets, x1 plus x2 plus out to xn, and then inside the set I would have vectors x1 plus x2 out to xn as well. So what does this say? It says that we're defining the Minkowski sum of a bunch of sets, in this case two sets. Now I put Minkowski in parentheses, the name of the guy who first invented this idea of adding up sets. I put it in parentheses because virtually no one actually calls it the Minkowski sum. I've only seen that fairly rarely. So most people just call it the sum of sets because there isn't any other obvious definition people use. So the sum of two sets is defined to be those vectors x1 plus x2 that I can form by having a vector from x1, a vector from x2, and adding them together. And we just call that capital X1 plus capital X2. In fact, also, there is an alternative, completely equivalent way to write this set, and you can see it's really the same. It's just written a little differently. And that says the set, the sum of the two sets, is the set of all vectors Z, the set of all vectors in the vector space, Z, that can be formed by adding up two vectors, one from the set x1 and one from the set x2. So this second way of writing this, I think, is perhaps a little more intuitive, sometimes a little easier to use in kind of thinking about and working analytically with the sum of sets. So with this definition, let's come back over here. We'll take this off and we'll look at several simple examples of simple sets, simpler even than the situation here. And then we'll come back after looking at those examples and we'll come back to our firm example and we'll develop that a little more fully. So let's take this off. Okay, so now let's do several examples over here of simple little sets that we're going to add up in R2. So first, let's just point out that in any, not just in R2, but in general, if I have, let's put this over here, if I have the vector, the origin, and I add that to any set A, that's going to be just the set A again, because according to our definition, if we add, the only vector we can add to A is the origin, and when I add that to any vector in A, I get the same vector back again. So it seems clear that's going to be, this is going to be like an additive identity, and of course, this is supposed to be a set, not a vector, but often when we have a singleton set, a single vector, we just write the vector, but technically that should be the singleton set consisting of the origin because we add two sets, not a vector plus a set. And let's point out that if we have any vector, any singleton vector x, and add it to a set A, that moves or displaces the set A by the vector x. Again, this is the singleton set consisting of just x. So let's actually see how that works. And we're going to be doing this, as I said, with sets in R2, so we can draw pictures, draw diagrams. So let's start off this way. So this is x2, this is x1. Now these are the components, not x1 and x2 is over here, so it probably could be a little confusing notation. The x1 and the x2 over here, those are distinct vectors. Here I'm using the subscripts for the components of a vector. And so let's, in the first case, let's suppose that A is the unit disk. So this is 1, and A is all the stuff in here, including the boundary. And let's say B is 3 and 2. So let's say 3 is this vector here. I'm not 3, B. B is this vector here. So this consists of just 3 and 2. And so what's B plus A, or A plus B? Well, as we said here, B plus A, B is just a singleton, so it's going to move the set A by the amount of that vector. So we're going to end up with a disk, but the center of the disk will be moved to this point here. So we're displacing the center of the disk to 3, 2, and we'll displace this point to a point about there, and we'll displace this point to a point about here, and so we will have a disk. This is supposed to be a nice circle. It's supposed to be just the same size as this. And so this set, the unit disk displaced to this point here, this would be the set B plus A. And of course, that's also A plus B. It's clear in the definition that that the addition of the sets is commutative. I could go A plus B or B plus A, x1 plus x2, or x2 plus x1, because the addition of vectors is commutative. So this would be the set A plus B, or B plus A, for these sets A and B. Now let's suppose that the set B, let me just take this off, and let's add in here, I didn't leave myself enough space, so I add in here the vector 3, 1. So now B is the set consisting of this vector 3, 2 and the vector 3, 1. So that's this point here. So now B consists of these 2 points. It's a 2-point set, and B plus A, or A plus B, is going to be the disk that we got before, but also I have to move or displace the set A also by this vector. So it means I have to displace everything that way. The origin gets displaced to here. The rest of the disk gets displaced to here. And so now A plus B is this whole set here, A plus the 2-point set B. Let's look at one more example in the same kind of genre here. Let's do that down here. Give myself a little more space, and let's have this be x1. This is x2. So this time, let's let B not be a finite set of just one or two vectors. Let's let B, and let's first actually do A. So let's put A here. This is 0 and 1. This is 1. This is 2. This is 3 and 4. And let's let A be this rectangle here. So A is this rectangle, which does include the origin, which is going to be convenient. And let's let B be this disk here that we got from forming A plus B before. But now we'll let that just be B. So that would be, here we have 2, here we have 3. And so that would be out here at 3 and 2, like that. And it would be the disk coming around here like this. So this is the same as this first disk I drew up here. So that's going to be B. And now I want to add A plus B. I want to see what A plus B looks like. So we could do all this analytically, but it's pretty straightforward here to just do the geometry. And that's all I want to do here, is to get the idea of how this works. So let me use a different color here. And I'm going to add every vector in A to every vector in B. And so the way I'll do that is I'll say, let's pick a vector in B, like this one over here, and let's add the set A to that vector, displacing A by that amount. And since the origin's in A, I can just pick this up and move it out here, move the origin to there, and then this is supposed to be vertical line here. I get, that's supposed to be this rectangle here. It's 2 units high and 1 unit wide. It is the displacement of A out to this point here. And then I have the same thing if I put the origin at this point. I have this comes down to 3, 2. This comes down actually here. I don't have them all looking the same size, okay, as they should be. And so we get everything in this rectangle. We get everything in this rectangle. And, of course, I could be sliding this origin along the boundary, and I would get everything in this sort of corner circle here, transposing the boundary up here. And then I could displace the rectangle out to here. Actually, it appears that when I did this one, I actually did this wrong. That wasn't right. This should have gone up 2 units and back down to here. So that was actually wrong. That's correct now, although it looks a little shrunken because I didn't let it go up far enough. So here I've displaced A over to here. And again, as I slide the origin along here, I'm going to have quarter circle. And then if I come down here, I'm going to have the rectangle A is going to go up to here, and so it's going to look like this. And again, we'll get this. So when I add A to each of the vectors in the set B, I get this kind of funny shaped sort of rectangle with rounded edges here, rounded corners, and this is A plus B, which again we'll write B plus A as well. And so it's everything in here. Okay, that's not a particularly useful example. I mean, we're not going to run into sets where we have a disk here and a rectangle like this. This is just an example that's, the purpose of it is to help us get a handle on understanding how it is that adding sets works. And we will come back and then do something similar for the production sets that we started with. So now we've taken off those simple examples, and I want to go back to talking about production and production sets. So recall in our example, we had an input good, which was steel, and we had an output good, which was trucks, and then we added another output good, which was cars. So let me actually indicate here, let's just say good number one is steel. And so X sub 1 will be the amount of steel that a firm, let's say, uses as an input. And let's say good 2 is trucks. So we were using Z for the amount of steel before, input, and Y for the number of trucks. And then when we added a second output good, we used Y1 for trucks, and we used Y2 for cars. And now I'm going to do all of this in Rn. So I'm just going to say let X be a vector in Rn, and that vector we'll interpret it, we'll use it as a description of a production plan, an input-output plan for a firm. So this, we'll say, is a production plan, or an input-output vector or input-output plan for a firm or in the aggregate or whatever. So it's a vector with n components. One of the components, let's say, is steel, another is trucks, another is cars. N might be 3, so we only have these 3. Let me even put in a fourth one here. Let's put in rubber. We could put in lots of different possible inputs for making trucks and cars, but I'm just going to put in these 4 goods. And now, in the example we did, we had 2 firms, firm A and firm B, and both of the firms, we said, were using steel as an input to produce trucks as an output. We used Z for this, as I said, we used Y for this. But now, if we want to aggregate across firms, or in fact, even sometimes we want to talk about the same firm at different points in time, what's going to happen is that some goods will be outputs for some firms, but inputs for other firms. And it might even be for a given firm that sometimes it's producing a particular good, but that same good might be something it uses as an input at a different point in time or a different point in the production process. So if that's the case, and we want to aggregate across the firms, we aren't going to be able to do that the way that we described before by using the Z and Y vectors, because sometimes, for some firms, the Z input will be the steel, but for other firms, that Z as an input will be trucks. So for example, let's see how we're going to handle that. So what we'll do is we'll say, in a production plan like this, we'll say if we have a component, like say the first component, steel, that's positive, that is going to represent an output good. So if good number 1 is steel, so X1 is a positive number, then that's telling me that's a production plan in which steel is an output. And then we're going to say if Xi is negative, that says we have an input good. So for the 2 firms we started with at the beginning, we said that steel was an output, so that would have been positive. Steel was an input, so that would have been negative, and trucks were the output, and that would have been positive. And let me point out here, this is in a vector X in Rn. So we have a vector X, and some components of X are positive. That's describing outputs. Some other components of X are going to be negative. That's describing inputs. Of course, the amount of input that goes in isn't a negative number. It's a positive number, but we represent it negatively to represent that it's coming in. And so that's what we do for input goods. And of course, there will be goods that in many production, if not all production processes that we actually see, there will be maybe plenty of goods that are neither inputs nor outputs that just don't get involved. The xi will be 0 for those goods. And so it'll actually be useful to keep track of the input and output goods in any particular x by the following kind of device. Let's let O of x be the set of indices, set of goods, set of indices such that xi is positive. So this is the set of indices on output goods. That is the set of output goods, and that's why O for output. And let's let capital I of x be the set of indices for which xi is negative. So that tells me all of the goods that are input goods. That's the goods whose components are negative numbers. So those are input goods. And again, there are going to be some goods typically that the index isn't either in O nor in I because xi is 0. It doesn't get involved in a production plan. And the really important point here to note is that both of these depend on x. So I put in a particular production plan, I can look at which components are positive and negative and know which are the outputs and which are the inputs. I look at some other production plan, some other vector in Rn, and I may have a different set of output goods and a different set of input goods. So for example, I may have one firm that, let's say, produces trucks and uses steel and rubber as inputs. Cars don't get involved. If it produces trucks, then this set is going to be just 2. That is, I equals 2 will represent the only output good for that firm, and the input goods for that firm will be 1 and 4. So I equals 1 and I equals 4 because these will be negative. Another firm may produce both trucks and cars using steel and rubber. So this set would consist of goods 2 and 3. This set would consist of goods 1 and 4. And then there may be another firm that produces steel as an output and uses trucks as an input to haul steel around. So in that case, the output good would be steel. This would now be 1. This would be 2 because trucks are used as an input. And let's say these are zeros, so they wouldn't show up either place. So this turns out to be a kind of powerful, useful way of modeling production. It enables us to model different firms that do different things, that some have particular goods as outputs, others have those goods as inputs, and we can still aggregate them by adding up their production plan vectors because, for example, we could aggregate, let's say, steel, where some firms it's an output, other firms it's an input. If we add those up, we get the net amount of output. Or if it's negative, that'll be a net amount of the input. So with this way of modeling production, let's go back to our original example with just the 2 firms that had only steel as an input, let's say, and trucks as an output, just the 2 goods. Let's say ignore the other goods. So in this case, n is 2. And let's draw the appropriate production sets for those 2 firms. So let's take off our definition and the equivalent statement of the definition, and let's do that over here. So here we have, now we're going to have to do the following. We're going to have, let's say, the x1 axis, and we're going to have the x2 axis. And I've written them in this kind of unusual way because for the firms we're talking about, neither firm is producing the first good as an output. It's an input for both firms. So this is actually going to be the same as the negative of the z that we had earlier. And this is going to be the same as the y that we had earlier. I may have actually written that right off the board here, so let me make sure I've actually got that visible. So let's first look at firm B. And firm B's production set, the set of all production plans or vector, input-output vectors that it can produce is going to be all of the input-output vectors on or below this curve, which is really the firm's production function. So here we can actually use the production function because we only have the one output of trucks. And so this is firm B's production set. Let's just write that here as XB. And then we have firm A's production set, which looks something like this. And so XB includes the stuff in here and the stuff down here. XA is just the vectors below the straight line here, which represents firm A's production function. And so these are the input-output vectors that are feasible or possible for the two firms. I've put them on the same diagram on purpose because now I want to aggregate the two, and I'm going to aggregate them by just adding up the two sets. XA plus XB would tell me all the aggregate input-output vectors that I can get from these two firms. And of course, that's just going to be the set XA plus the set XB, and we already know how to do that. We've done that in some simple examples. Here, since the origin is actually in both sets, but in particular, the origin is in the XA set, let's say, I could now take that XA set, move the origin, slide the origin along the boundary here, and I will trace out all of the vectors that are a sum of a vector in XA and a vector in XB. And what I will get is that I won't get anything added until this gets up to the point where the slope of the production function actually for firm B is 1/2, because remember the slope of this is, well, actually it's minus 1/2 here because it's going this way. So in fact, let me actually use a different color here. Let's actually, I think I want to use this color here. So let's draw this about like this. So this orange curve, which coincides with the XB curve up to here, and then it's a straight line corresponding to the XA curve displaced, that would be the set X equals XA plus XB. So that would be the aggregate production set for these two firms. So now what I want to do is I want to look at profit maximization by the individual firms and the maximization of profit for the aggregate set, profit maximization in the aggregate. All right, so let's come back over here and look at the profit function. So profit over here is going to be, I'll use pi as the name of the profit function, and it's going to depend on the production vector x. So, and this is going to be in general now in Rn. So profit, of course, is just revenue minus cost. Simple but really important thing to not forget. Okay, revenue generally depends only on the output goods, but that means it depends on all the goods. It's just that we can suppress what happens with the non-output goods, and similar for input goods on cost side. So we can write these both as depending on the whole vector x, and in particular, revenue is going to be, well, it's going to be, now I'm going to assume from this point downward that I'm looking at price-taking firms. So let me make a note of that so we don't forget it. So from here down, this is going to be price-taking firms. By that I mean firms that take prices given, so the amount that they produce or the amount of input they use doesn't affect the price of the input or the particular output. And if that's the case, then revenue is going to be the sum of the price of each output good times the amount of each output good that is produced and sold, but I can only be adding here over the output goods. I don't want to add in the input goods when I'm talking about revenue. And cost, well, I'm going to subtract off the cost. So the cost is going to be the sum over all the input goods of PI times the amount of input that's used. But of course, we're representing inputs as negative numbers, and the actual amount of the input is a positive number, so I have to put in here minus xi. So this would be like the z that we had over here. Notice here I had xi is minus z, minus xi is like z. Okay, so minus xi is the positive amount of the input being used for input I. And of course, this is just the sum from I equals 1 to n, the sum over all the goods of pi times xi. These two minus signs cancel one another out. And of course, there are going to be some goods that are neither inputs nor outputs, but those are going to be ones where the xi is 0. So that's not going to make any difference. I can include them here because xi will be 0. And of course, this is p dot x, a linear function. So a linear function. So what I want to do here is I want to use this profit function and apply it to the two individual firms and see what happens if they both maximize profit. And I want to apply the profit function to the aggregate set and see what would happen in the aggregate if we maximized aggregate profit and see how they compare. It's going to turn out that they're the same. And so that is the content of this, our first optimization theorem. So notice what the theorem says here. It says we've got a linear function on a vector space V. Over here, of course, the vector space is Rn. It's a linear function, f, in general. Over here, the linear function is always is a convex combination of the vectors of the, well, actually it's a dot product, so it's not a linear combination, it's the dot product here. So linear function, we know from what we did with linear functions that linear functions are always characterized by a matrix times a vector. And in this case, since we're mapping into R1, profit is one-dimensional, it's going to be a 1 by n matrix, if you like, of p's, p1, pn. And so the theorem here says that if we have a linear function, and here we don't have just two, we actually have m sets, then we have a vector that maximizes profit in the aggregate if each of the individual vectors that get summed up to the aggregate vector, each maximizes the linear function on the individual set xi. So this is a general theorem that tells us that when we are looking at maximizing a linear function, that's important, and I'll come back to that over here. When we're maximizing a linear function, we could maximize that function on the aggregate set, as in the first line of the theorem, or we could maximize that function on the individual sets, and we would get the same outcome, and we would end up with the same vectors being maximizers, whether we do this individually, one after the other, or we do it in the aggregate. Now, coming back over here, let me write that theorem. Let me write that theorem as it applies to this situation where we have, we're in Rn, not just an arbitrary vector space, and where, therefore, a linear function has this form. So here, the theorem would say, or the theorem does say here, that, and I'm only going to do this now for two firms because I want to apply it to our problem here. So we would say that XA, and I'm going to use superscripts, and I'm doing that because I want to continue to use subscripts to keep track of the goods. So for firm A's production plan plus firm B's production plan, the sum of these two plans maximizes P dot X, a linear function, on capital X1 out to capital Xn. Actually, in this case, let's make that Xm as we did over here. Okay. Well, actually, here we only have two sets. So let's actually fix that. Let's change this to square with what we're doing with just the two firms. So let's say this is XA plus XB. So if I have two firms, this production plan for the first firm and this production plan for the second firm added up, aggregated, that aggregate vector in Rn maximizes the value function, or the profit function, on the sum of sets if and only if X hat I maximizes P dot X on capital Xi, where here I is just A and B. Now, of course, if I had more firms, I probably wouldn't use letters. I'd use 1, 2, 3 out to M firms, let's say. And so I'd have the sum of M production plans, I'd have the sum of M sets, and then I'd have my maximization here being a maximization of the value function, the profit function, for each firm. So we have this. So finally, let's bring this back over to our first example, our example of the two firms with the specific production functions. Let's take back off the general theorem and just keep this theorem because we're going to want to use this space down here. So we'll take off this theorem here. And so let's note that the profit function here, in fact, let's even just note here that for the two firms, the profit function is just pi of x equals pi of x1 plus x2, which is p1 x1 plus p2 x2. And that's true for any production plan, whether it's an aggregate plan, so this is aggregate x's, or whether it's a production plan for firm A, so this would now be firm A's production plan, and this would be firm A's profit, or it's firm B's production plan, and that would be firm B's profit. So the profit function in any case looks like this. And so the isoprofit contours, the contours of the profit function over here, look something like this. They're, of course, all parallel to one another. So these are the contours of the profit function, and the slope of these contours, given that these are the prices, and of course, this is just a generic picture. I'm going to make these flatter or steeper depending on the prices. But depending on the prices, the slope here is minus P1 over P2. So the last thing I want to do here is I want to actually carry out the maximization for each of the two firms and the aggregate maximization. So let's go down here and let's look at the maximizers. So let's start off by, let's perhaps start off by defining well, I'm not sure I'm going to use this, but let's actually define rho to be pi 1 over pi 2. I may just continue just to use the fraction P1 over P2, but I might want to use this, this rho here. So let's first look at firm B. So for firm B, let's just note that the profit for firm B as a function of, and now I'm going to write the profit. This is a little bit of an abusive notation here. So the profit actually depends on the entire vector x1 and x2. So I'm going to express the profit as a function just of the output, assuming that the input is whatever it takes to get that output. So I'm assuming that I'm on firm B's production function here. And so I know that since x2 is the square root of x1, x1 is the square of x2. Or actually, the negative of x1 is the square of x2. So this is going to be the price of the output good times the amount of the output good minus the price of the input good times the amount of the input good that the firm's using, but the amount of the input good, we're assuming the firm is going to use just the right amount of input to get that output, if you like, the minimum amount of input to get that amount of output. So that means that the amount of input here is going to be minus, this is going to be x2 squared. It's going to be minus x2 squared, but of course I'm not squaring it. The minus is going to disappear here. And so this is just, let's actually write this and rewrite this as P2 x2 minus P1 x2 squared. So now I have something that's a function of just x2. I can take the derivative. Again, I want to emphasize I'm just kind of a little bit of an abusive notation since I'm rethinking the profit function as having only the one variable. And so the derivative of this is going to be P2 minus 2P1 times x2, and that's 0 if and only if x2 is equal to P2 over 2P1. I guess that's, if I use this rho here, that would be 1 over 2 rho. I don't know if that's necessary here. Okay, so that tells me what x2 is going to be, and that's what x2 is going to, and let's actually add x1 in here. x1 is going to be the negative, because we're using negative numbers for inputs. That's going to be minus x2 squared. So I know what the firm B's production plan will be if it's maximizing profit as a function of the prices. Basically tells me its input demand function and its output supply function is a function of the prices. And now let's look at what happens when the profit contours, the profit function has their steep contours, their flat contours, and so on. So let's go down here and say if P 1, let's actually write that this way. Let's say if P1 over P2 is bigger than a half, so this is the case where the profit contours are steep, and in fact they're steeper than the production function for firm A because its slope is minus a half. So if this is the case, then we know that firm A maximizes its profit by choosing to not produce. Because these profit contours are steep like this, it's trying to get on the highest contour, so it would have XA hat, let's say, would be 0, 0, X hat, the sum of XA hat and XB hat, in fact, it's right, this is X2 hat, X1 hat, for firm B. I didn't put the superscript on here, kind of be squeezing it in there. So this would be equal to just XB hat, which we've already figured out. So that tells me that if the prices are like this, if the input price is bigger than 1/2 the output price, then I'm going to have firm A not producing, and the aggregate production will just be firm B's production. If P1 over P2 is less than a half, then we have, there's no maximizer on XA because the profit contours are flatter than this, and I can always increase the profit by going further and further out, and there isn't going to be an input-output vector that maximizes profit. So no maximizer on XA, but also no maximizer on the aggregate set for the same reason. So, or on the aggregate set. And of course, it's still the case that firm B will be producing this amount here if it's maximizing profit. But that is not going to be a profit, not going to correspond to profit maximization on the aggregate set because there is no profit maximizer on the aggregate set. And last, let's look at what happens if P1 over P2 equals 1/2. If P1 over P2 equals 1/2, then our profit contours here, let's use pink, our profit contours have exactly the same slope as firm A's production function, and that means that every single point on this straight line boundary of XA is going to yield profit equal to 0, the same profit as this. So all of these production plans have profit 0, and that is the largest profit that firm A could earn because all the other input-output plans are on a lower profit contour, and so they yield negative profit. So in this case, it would be, we would have any XA such that XA2 is 1/2 XA1, and I should make that minus XA1 because we are doing inputs negatively here, so this should be equals this times minus XA1. Any XA that does that yields the profit of 0 for firm A, and that is the maximum for firm A. And again, it's the case that firm B is going to do this, and then this, if P1 over P2 is 1/2, we have X hat B, as you can easily check here, since P1 over P2 is 1/2, we're going to have, this should be a P1 down here. Since P1 over P2 is 1/2, P2 over P1 is 2, and I have 2 over 2, so I have 1, and I have 1 here, so this is going to be 1, 1, which means that firm B will actually be producing right here. This is going to be 1, and this is going to be 1. And so I actually can work out the maximizing production plans for each firm, and you can check easily that the sum of the two maximizers is always going to be the maximizer on capital X, which we've said here, but you will have to check, but it's straightforward to do. So that gives a pretty good idea of several important ideas here in economics and to some extent in mathematics, but it's really more economics. We have developed an alternative way of modeling production by using negative numbers for input goods, so that production, and we've also been using production sets instead of production functions, although we can do them interchangeably in the case where there's only one output. As soon as we got more than one output, we really have to go to production sets. So we got production sets. We've got this approach here, which means that the production sets will look like this. Or of course, alternatively, if I happen to have a firm that's producing, well, in fact, let's say in this example, this was steel and this was trucks. And so if we happen to have a firm that's using trucks and their inputs for producing steel, then the production set would be down in this quadrant down here and look sort of like these, but maybe something like this or something like this. And then we would want to add those sets to figure out what we could do in the aggregate. So we've got this new way of modeling production, and we have the notion of adding up sets in a vector space, and in particular in a Euclidean vector space. And we have our theorem, of which this is just a special case with two sets and in Rn. So here we should have said that this is a theorem in Rn. And we have the general form of the theorem in vector spaces. So we've developed quite a few things here. So that's it for today, and we'll see you next time.